Well, I'm actually, you'll find it odd that I'm giving this talk, but a remarkable energy source is being overlooked, so I thought I would. With apologies to Cindy Vandover and Karen Jacobson, who made this fine illustration of a deep sea hydrothermal vent field. The essential astrobiological assumption is that there are more things in heaven and earth than are dreamt of in your philosophy, whether you're in Denmark or someplace else. And what I wanted to bring light to, if you will, is a different habitat and one that's not being considered widely in this field, although it was invested in specifically for that purpose. In the beginning was a shrimp. A novel eye and an eyeless shrimp from the hydrothermal vents in the mid-Atlantic brought you Rummicaris exoculata. Exoculata because it doesn't have eyes where shrimp normally do, but instead has these two pointer arrays on the back of the shrimp. And it was kind of an interesting adaptation because it can be traced that they're actually hooked up the same way that regular eyes would be, but they're obviously quite different. And if you were going to shoot down satellites with a Navy ship, you'd probably recognize those, but that's not what the shrimp do. The question was, why do they have these eyes in the first place, and why do they have them on their backs? It turned out that they were most sensitive to light around 500 nanometers, which is visible. And the availability of visible light isn't something that's obvious to people in Alvin with the lights on in particular, but our eyes aren't good enough to see things like that. So the question was, okay, if they're not actually, talking to each other or using light for social networking, what do they do and what's available? This was brought to bear, and NASA got involved at about this point, a light and thermal environments workshop that was held with Ridge at Hui way back when, and Michael Meyer got to go and I didn't. But I was very interested in this. It was clear that if there were light available on the seafloor, that there might be something that used it. And so Ewan Nisbet, Joe Cannon, Cindy Vandover got together and published this little note in Nature about the origins of photosynthesis. And the idea is if you could do photosynthesis on the seafloor, then there might be a place for photosynthesis to kind of hide out in the presence of large impact events that might go ahead and boil off the surface of the ocean and make it very difficult to be a photosynthesizing organism under the constant bombardment. So that's the basis of this. But the idea was, okay, you got some visible light on the seafloor. Is it enough to do anything useful with? Let's go measure the light. And of course, where were you going to measure this? Here's a Rummicaris exoculata having its eye strained by Alvin on the seabed, tag field. A Scotsman described this as in kind of an uncolorful way as reminding him of maggots on a piece of meat. Unfortunately, if you have a meat that looks like that, you should have thrown it away long ago. This is a kind of a generic hydrothermal vent picture. I think that's 9 North. And one of the interesting things in concert with John Delaney is that they found out that vents in fact do glow, and they glow in the near infrared. And of course, from a black body radiation standpoint, that makes perfectly good sense. Where would that glow be most intense? And one of the places that people look at are these flange pools that form on the side of some vents, where basically there's a deposition of material and the hot water leaves a small kind of static pool underneath there. There's a slope often here, and in fact, on the Juan de Fuca, that's where we looked for light on the seafloor. So this is a camera called Alice, which is there measuring light emittance. This is the Lobo flange. For those of you who have been to Juan de Fuca, you could remember it. And it's dark under there to us, but it's not dark under there if you're looking in the infrared. And what's kind of fun about this is that this is the little dotted line that represents what Alice can actually see. There's visible light, not in this particular case much at the area where the shrimp is the most absorbent, but and it goes up to high fluxes of infrared light. Calculated photon flux is in the order of 10 to the 10th, depending on how you look at it. And that's a lot of photon flux in photons per centimeter squared per second. So there's a possibility that something could actually use that light brought to you by the good graces of hot water. Okay, so what light at the seafloor? The fact that visible light is present suggests that at black smokers and not flange pools suggests that there's a source of visible light that's not related to the hot water itself, but in fact has something to do by triboluminescence, precipitation of some kind of chemical environment. But the existence of light suggests that there might be, in fact, enough light for photochemical processes, photobiochemical processes. And that might be that something could live on that light. And flanges in particular are a good place for that because with a 1 meter square or more opportunity to spread that light around, you can actually have a cozy little place at the bottom of the seafloor. And it's very similar to the kinds of light that actually drives phototrophic sulfur bacteria in the Black Sea. So this was from a paper that was put together on the basis of the Alice interactions, and that was in the next thing that, of course, was obvious to do was to go look for something that actually had to use that light. And so Beatty et al. In the East Pacific Rise found green sulfur bacteria that don't mind the deep and, in fact, live under a flange pool on a black smoker chimneys and are capable of doing just about everything that you'd want a microbe to be able to do, except for they can do it near the hydrothermal vent stacks. They don't do it in the waters around them. They're anaerobic in function, but they can stand oxygen. And in particular, in the dark, they can stand oxygen. And they were isolated with light sources that were pretty dim, kind of daytime, not even daytime, but fluorescent lighting in a lab. And only certain kinds of things enhance their growth, but they are not found anywhere else to date than down at the East Pacific Rise. So the obligate photosynthetic bacteria is an interesting concept, and it's something that we could actually look for elsewhere. They're anaerobes. They can provide you with a comfortable lifestyle, especially if you're in the Juan de Fuca or places like that that have kind of a minor energy imbalance, and you tip it over. And of course, everybody goes, "Oh, that's fine," but what kind of photosynthesis is this? It's not oxygenic photosynthesis. What they're doing is basically using the light to run a proton pump that allows them to make ATP from ADP and charge that up. So they use the energy almost directly. And this is really fascinating because, of course, that's what you'd want them to be able to do. In an ancient environment before the development of oxygenic photosynthesis, that's probably as good as it got. And in a place like Europa, it might actually be happening. We have abundant hot water, apparently, or at least some people think so. We don't know how to find it yet, but we'll get there. So the light comes in, runs the pump, allows you to make ATP from ADP. Going to look for this, however, ran into a couple of other discoveries, and in particular, Z. Kolber trying to use a infrared fast repetition radiometer, fluorometer, that he and Paul Falkowski had put together. They tested it out on the way down to the Galapagos Ridge and found that they got anoxygenic photosynthesis everywhere. Similar, Ed DeLong and his colleagues also discovered that there was a lot of proteorhodopsin phototrophy going on in the ocean, things that hadn't been measured before. In the case of Z. Kolber and company, they estimated that 2 to 5% of all photosynthetic electron transport in the upper ocean is acquired by this mechanism. So not the breaking of water that you're used to, but just kind of scavenging ADP to ATP, and doing that regular and getting rich as a result. So could those processes be at work in Europa? If there's hydrothermal venting, certainly they could be. If hot water on Europa can be just as hot as hot water on Earth, in fact, if the ocean is as deep as we think it can be, uh, perhaps even hotter, although 407 degrees Celsius gives you a pretty bright light source. The caution in exploration is important, of course, because you wouldn't want to go ahead and go to a deep-sea hydrothermal vent on Earth and then go try to look for these things on Europa without cleaning up your spacecraft. But that's another life that I've had and worried about that. So the question is, what do you look for from a lander to be able to tell whether or not something's doing this? Can we find ATPase run backwards? Can we find anything that's resembling ATP? And that's the challenge for Kevin and his company. But I submit to you, it wouldn't be a bad place to look. So a short paper, I wanted to point out that all these environments on Earth are subject to some kind of threat right now. Depending on how people want to mine these, the reason Cindy's not here is that she's spending all of her time trying to protect deep-sea hydrothermal vents from exploitation by mining interests, whether in back arc basins or elsewhere. And so something to consider, don't let the miners take your study site away from you. Thank you.
Thank you, John. Time for questions. Jeff.
Your description of the zone of illumination and sort of size of the flange environment got me thinking of like the solar arrays in the Southwest that have mirrors reflecting it back to one central point. So I'm wondering on the mineralogical side if there's a way to sort of focus some of these photons, whether through the structure of the mineral itself or the reflectivity or the optical properties of what would be at these vents.
Well, for the visible light, sonoluminescence, triboluminescence, chemical reactions are all possible. And that's been, seen as an additional component of this light when measured with ALICE. In terms of the black body radiation associated with the hot water, it doesn't require any special things other than having gotten hot enough. So the specific cause of the triboluminescence or the sonoluminescence at a particular vent site is not generic enough, but it's clear that collapsing bubbles, et cetera, I mean, if it can take out a dam in the southwest US, which it has in the past, that sort of power is actually something that comes out of the top of hydrothermal vent stacks. So even without a flange pool, which is a terrible place for visible light, but a great place for enough light to drive photosynthesis, you've got a lot of power there going on, and you could actually do it a couple of different ways. The dam was the you have to read about the Grand Canyon when they had to open up all the stops because the particular spillway was actually degrading in cavitation, and all the concrete was leaving and the river turned red, and they said that's not good. Anyway. All right, thank you.
I've got one before you go.
So
you're talking about if there's abundant hot water, then there's plenty of scope for photosynthesis. How does the photosynthetic radiation drop off with temperature? I'm thinking like Andy Fisher was making that point yesterday of like you can have a chimney with an orifice with very high temperature, or you can have the same kind of cumulative heat flux over a distributed area at lower temperature.
yeah,
Does that impact the potential for photosynthesis depending on how the water's coming out of the ground?
it does, and it's just basically a black body radiation curve. I mean, if you've got hot enough, these particular green sulfur bacteria were isolated from a vent that was at 330 degrees Celsius. So you can be pretty cool and still have enough light if you want to get close enough, and it's kind of a balance thing. I mean, we know the shrimp are looking at different things because they're looking at visible, and that's probably for their social networking as much as anything else, because the shrimp don't like to get into the real hot stacks, but they don't have to actually get all that close. If you're a bacterium and you've got a place to lodge and it's right next to something that is putting out even a small amount of light, you can use it to kick over this kind of proton pump driven photosynthesis.
Okay.
So,
Mark.
So I agree with you that it's important not to overlook any potential sources of energy, whether it's photosynthesis or
It's an energy distribution system.
Right. I guess one of the reasons why you might want to overlook it is because presumably on Earth it's been difficult to evolve to be able to perform photosynthesis. But I'm wondering to what extent you'd think it would be feasible to evolve systems like this at low energy flux at a seafloor, under a huge layer of ice. And
The energy is available, and systems can evolve to use it. We know that in the Black Sea, there are organisms that use light at these kind of dim levels, and they seem to be, rather pervasive there. It's thought that this kind of photosynthesis is actually something that has been evolved several times in several different habitats, but particularly, it's very hard to believe that this green sulfur bacterium is a linear descendant of something that always lived in a hydrothermal vent site. And so going onto the land and coming off of the land would be an easy thing for this kind of photosynthesis to require. And you can read the paper by Beatty et al., but basically they have that in the discussion.
All right. One last question. Tori in the back.
Energy guy.
Yeah, I could be last. Just a real quick question. Has anyone tried to walk out of a limb and estimate what this black body photon flux might look like globally, rather than on a event-specific basis?
I don't think anybody's done it globally, but if you give us the distribution of global hydrothermal vent sites, I'd be happy to do that.
Fair enough.
Okay, thank you.